In this video, we continue our understanding of Le Chatelier's principle by looking at an equilibrium in the gas phase. Right? So the equilibrium is going to be nitrogen dioxide generating dinitrogen tetroxide, which is a very well-known equilibrium in the gas phase. Okay? It's a dimerization of nitrogen dioxide to get this molecule. Now, at equilibrium, at a particular temperature, we can say that the pressures at equilibrium would be 0.90 atmospheres and then 0.10 atmospheres. And from here, we can go off and calculate what the equilibrium constant would be. Okay, that equilibrium constant is going to be the pressure of products divided over the reference pressure, which will be at 1 atmosphere, and then all of that is divided by the pressure of NO2 divided over the reference pressure, and then squared. Okay, so in the short form, this is simply going to be the partial pressure of N2O4 over the partial pressure of NO2 squared. We usually write a sub P subscript there in the equilibrium constant when we're dealing with gases, and plugging in the values that we have right here: 0.1 atmospheres for dinitrogen tetroxide and 0.90 atmospheres for nitrogen dioxide. This returns an equilibrium constant of 0.12. Okay, great. So this is just the preliminaries to frame the discussion of Le Chatelier's principle. We're now ready to modify this equilibrium. Okay. What we're actually going to do is as follows. Suppose that we have these gases inside a cylinder with a movable piston. We can either lift or lower. Right, so here you would have your NO2, which I'm going to draw as dots, and occasionally you will have an N2O4 molecule, which I'm going to draw as circles. Right, so that's more or less a representation of the actual concentrations. And then what we're going to do is actually decrease the size of the volume by 1/2. Okay, so we're going to push this piston down such that your equilibrium now is going to be half the volume. All right, so you will have exactly the same amount of molecules of each. Okay, but they will be in a container that has a volume 1/2 of the initial volume. Okay, so the question is, does this change the equilibrium, and if there's a modification to the equilibrium, where will be the shift in the chemical reaction to regain equilibrium? Right, so notice that if we don't change the temperature, if we don't add any moles of any of the reagents, effectively what we're doing is we're doubling the pressures of each one of them. Okay, so this will be our equilibrium, initial equilibrium. Then once the modification takes place, now the pressures double because the volume has halved. Okay, so that will be the new pressures, which we're going to call initial, after the modification, which is to increase the pressure here. So the question is whether we will be at equilibrium or not. We can calculate the reaction quotient for these new partial pressures, and then what we'll have is that this is equal to 0.20 over 1.80 squared, and the value that you get from this calculation is equal to 0.06. Okay, so clearly Q is not the same value as the equilibrium constant is actually lower. So in order to regain equilibrium, what has to happen is that some of the reagents have to go into products, and what that means is that the equilibrium has to be displaced from left to right. Okay, that will be the prediction. Then you can set up here your eyes diagram, and then that would mean that this has to grow, this has to decrease. Notice that we have here a -2 because the stoichiometric coefficients are 2 and 1, and then you can carry out the calculation and predict how this is going to end up, right? So the equilibrium calculations tell you that at the end, this is going to be 1.6 atm and then 0.30 atm, more or less. Okay, so clearly it is true that the equilibrium has shifted from reagents to products, left, right, after the disturbance. Okay, so this is great, but we actually have not talked about what the prediction of Le Chatelier principle would be. We simply have carried out our equilibrium calculations and predicted where the new equilibrium will lie. how would the Chatelier principle deal with this situation? Well, let's analyze what the disturbance has been to the equilibrium. What we actually have done is to increase the pressure, right? So in the spirit of the Chatelier principle, if there's anything that you can do to lower the pressure, then that would be something to alleviate the disturbance that you have introduced. Right, so when we examine this equilibrium, we can say, is there any direction that you can shift so that the total pressure is lower? Well, and it's pretty obvious that, well, if you reduce the total amount of molecules in the gas phase, then the pressure will come down, because the number of moles is directly proportional to the pressure if the temperature and the volume are the same. Right, so notice that we actually have a clear way to reduce the number of total molecules in the gas phase and then lower the overall pressure, and that is to go from reagents to products, which is exactly what we have predicted with our equilibrium calculations. So once again, the prediction from the Chatelier principle is borne out by the calculations, which indicates how useful that very simple principle is in predicting how a system will shift once a disturbance has been introduced into an equilibrium.